Welcome to EK307 Electric Circuits. This video will help you prepare for the lab experiments, resistive networks, and Thevenin equivalent circuits. The laboratory goal is to reverse engineer a mystery circuit. The learning objectives include parallel and series resistor combinations, circuit modeling, and the Thevenin equivalent circuit. Some of the tools you may require to do these lab assignments include a voltage source, a multimeter, a waveform generator, and an oscilloscope. There are two related tutorials that you may find useful. One is called Resistive Circuits and Ohm's Law. The other is called Thevenin equivalent circuits. You can find links to these tutorials at the bottom of the EK307 website. Before we go over the lab assignments, let's first review some of the properties of resistors. Specifically, how do resistors combine when they are connected in series? They simply add. For example, if we have one resistor of value R1 and another resistor of value R2, and we connect them in series, the net equivalent resistance is equal to the sum of the individual resistor values. Two resistors in series produces an equivalent resistance equal to the sum of the individual resistor values. How do resistors combine when they are connected in parallel? The answer is a little bit more complicated. They combine according to the formula R1 in parallel with R2 is equal to the product R1 R2 over the sum R1 plus R2. This formula is not as complicated as it may seem. If you recall, you can express the value of a resistor in terms of its conductance G, which is equal to the reciprocal of the resistance. When two resistors are connected in parallel, the equivalent resistance of the combination is given by the sum of the individual conductances. The conductances add. Adding two conductances together, if one goes through the math, yields the familiar formula R equivalent equals R1 R2 over R1 plus R2. We'll refer to this formula as the parallel resistance formula. The first part of the lab asks you to determine which of the networks A, B, C, or D is inside the mystery box that you will be assigned by the lab TA. You will be given one of the following networks without knowing what is inside, and it's your job to determine which network you have. To illustrate one possible method of determining which network you have, let's suppose that you are assigned network A. You will next make some measurements on the network to see if you can figure out which one it is. The key to this problem is that all resistors have a value of 10 kiloohms. Therefore, the net resistance of any network shown above, measured between terminals 1 and 2, will be determined by series and parallel combinations of 10 kiloohm resistors. Let's review how to measure resistance. It's very simple. We start with the multimeter located on your lab bench. And remember to press the ohm 2-wire switch to set the meter up to measure resistance. Here's a magnified view of the connectors on the panel of the multimeter. And to measure resistance between nodes 1 and 2, we simply connect one wire from the high terminal, say to terminal 1 of the network, and the other wire from the low terminal to, say, terminal 2 of the network. Now let's suppose that you've made these connections and the ohm meter reads 6 2/3 kiloohms. How can you determine which of the networks you have? Well, the answer is that you have to analyze each of the individual networks to determine and predict what resistance you would measure if you had that network. In our case, we're assuming that you've read a resistance of 6 2/3 kiloohms on your meter. And again, we want to ask the question, does this value match any of the networks? And of course, it had better match at least one of the networks shown on the lab handout, or something's wrong. Let's look at network A and predict what the net resistance would be for this network. It's fairly straightforward to do because the two 10 kiloohm resistors on the left-hand branch can be added together and be represented by a single equivalent resistance of value 20 kiloohms. Simply connecting the two 10K resistors in series produces that equivalent value. We can next analyze the resulting circuit by computing the value of these two resistances in parallel. Specifically, the equivalent resistance is equal to the parallel combination of 20 kiloohms and 10 kiloohms. And if you do the math, you come out with 6 2/3 kiloohms. In other words, this specific network A can be modeled as a single resistor of value 6 2/3 kiloohms. So the answer to which network you've been assigned because you've measured 6.66 kiloohms is that you've been given network A. If you had measured some other value of equivalent resistance between nodes 1 and 2, that would indicate that you would be given network B, C, or D, and of course you will have to go through the calculations to predict the equivalent resistances of these other three networks. Let's analyze one of the resistor networks from level 2. These are a little bit more complicated because there are 4 nodes or 4 terminals of the network to contend with. So we're going to analyze this circuit and come up with a prediction method using a slightly different technique. Let's suppose, for the sake of example, that you've been given mystery network B. Let's make a matrix of measured resistance values between the various nodes. Here's the matrix table, and the resistance measured between any two nodes will be placed in this table at the box that is at the intersection of the column of one node and the row of the other node. Here's the first example. The ohm meter is connected between nodes 2 and 4, and we can predict what the ohm meter will read in this case because the circuit is completed by two 10 kiloohm resistors in series. The net resistance of the series combination is 20 kiloohms, and so for this network we would expect the ohm meter to give us a reading of 20 kiloohms. Note that the resistors connected to terminals 1 and 3 don't have any bearing on what we measure between nodes 2 and 4 because they're not connected to anything. Current cannot flow through them. They don't affect the circuit in any way. So having made this measurement between nodes 2 and 4, we can now enter 20 kiloohms into the terminal 2, terminal 4 box in the matrix table. And of course there are 2 such boxes because each node is represented by a row and a column. The next measurement that we're going to look at is between nodes 1 and 2. In this case, there's only one resistor between those nodes, so we expect the reading to be a simple 10 kiloohms. And let's now enter that value into the table at the intersection between nodes 1 and 2. There are 2 entries again. Continuing on, between nodes 1 and 3, we would expect to measure a net resistance of 30 kiloohms because there are 3 10K resistors in series. So indeed, we would measure 30 kiloohms between nodes 1 and 3, and we can add those values to the table of what we would expect to measure for this particular network. Continuing on between nodes 3 and 4, we would see two 10 kilo ohm resistors in series, and we would expect to measure 20 kilo ohms between nodes 3 and 4. Let's add those values to the table. One last one, just to be thorough. Between nodes 1 and 4, we would be connecting to a pathway, again, of 3 resistors in series, so we would expect to see 30 kilo ohms on the ohm meter. Let's add those values to the table. In this final slide, I'm simply going to complete the table with all the values we'd measure between the various nodes in the case of network B. And when we filled in all the values of the matrix table, we have a unique table that will apply only to network B. And the networks have been devised such that this is the case. Every table that you can compute for each of the networks is unique to that network. So in this case, the network B table, if we were to measure all the various values, would indicate that are shown in the table between the various nodes, would indicate that network B is the one we have. And so when you do this part of the lab in level 2, you'll have to construct a similar matrix table for all of the 4 networks A through D, make your measurements on the network you've been assigned, and see which table of measured values matches the table of calculated values. Then you'll know which network you have. Part 2 of the lab asks you to determine the Thevenin equivalent at port AB, that is the Thevenin equivalent seen between the nodes A and B, looking in as shown by the pink arrow. Now in this case, the network is set up by a different mystery box, not the mystery box used in part 1, but one that is meant to be connected to a 6-volt source, the 6-volt source on your lab bench. So in this experiment, you'll be given one of several hidden networks, which when you connect it to the 6-volt source will form a circuit having a unique Thevenin equivalent. Every mystery box will produce a unique Thevenin equivalent as seen at nodes A and B. Now it's important to remember that this 6-volt source is not the Thevenin voltage. However, it is responsible for establishing the Thevenin voltage seen between nodes A and B. In other words, V Thevenin in the model is derived from the 6-volt source and will be some fraction of 6 volts. Let's talk about one possible method for finding the R Thevenin seen between terminals A and B. A very easy way to do it is simply to set the 6-volt source to 0. Now because V Thevenin in the model is derived from the 6 volts, the 6-volt source, setting the 6-volt source to 0 will also set V Thevenin to 0. In that case, you can simply take your ohm meter and measure the resistance directly between terminals A and B, and that will give you the value of R Thevenin. A possible method for finding V Thevenin is simply to measure the open circuit voltage. We do that by setting up the multimeter to be a voltmeter and connecting the positive and negative terminals to nodes A and B, respectively. Now you may recall that the resistance seen looking into the voltmeter is very high. In other words, it's almost an open circuit and no current flows from the circuit into the voltmeter. I may have said ohm meter a moment ago, I mean voltmeter. Therefore, the meter reading is the open circuit voltage. There's no current flow through R Thevenin, hence there's no voltage drop across it. The only voltage measured between nodes A and B is V Thevenin. So in this case, V Thevenin of the network, if we measured 3.2 volts, would be just that value. Open circuit voltage, Thevenin voltage are one and the same. In this case, in this example, we have found R Thevenin and V Thevenin by measurement. There's another way that we can find R Thevenin, and it's the recommended method for finding the R Thevenin of the waveform generator in level 2. Now just to review what comes out of the waveform generator, its output appears at this BNC connector. And inside the instrument is a waveform generator that we can model by a Thevenin equivalent. V Thevenin in reality is some time-varying voltage source, and R Thevenin is going to be some fixed value. The BNC connector has a center connector and its outer shell. The positive side of the Thevenin circuit is connected to the center connector, and the negative side of the Thevenin circuit is connected to the outer shell, which is also the earth ground of the instrument. We find V Thevenin by measuring the output between the center and outer shell with an oscilloscope. In other words, we measure the output at the BNC connector. Like the voltmeter, the oscilloscope has a very high input resistance, and it appears as essentially an open circuit to the waveform generator. So we can use it to measure the open circuit voltage, which is one and the same with the Thevenin voltage. Here's another way for finding our Thevenin that involves adding resistors, external resistors, across the output terminals of the waveform generator. Suppose we were to take a resistor and connect it across the terminals of the BNC connector. We would need some sort of adapter or perhaps some clip leads on a coax cable to do that. When we add a second external resistor, we create a voltage divider that provides a fraction of V Thevenin at Vx. And you remember the voltage divider formula says that the voltage across this pink resistor, Vx voltage, is going to be equal to V Thevenin multiplied by the ratio of the pink resistance to the sum of the two resistors. Now let's suppose that we happen to choose the value R Thevenin for the pink resistor. Well, in that case, our voltage divider divides V Thevenin in half. Vx will be equal to V Thevenin over 2 in this case, again by voltage division. So the strategy for this method of measuring the Thevenin resistance is to apply different resistors to the BNC connector until the open circuit voltage is reduced by half. And then we will know that the resistance being applied is the Thevenin equivalent resistance. Well, that's about it for this tutorial. I hope it's been helpful. Two more things to remember. One is that you should learn lots in doing the lab experiments, and most importantly, you should have fun doing them. Good luck with the experiments.